Good morning and welcome to this lesson 3, which is a very short one, perhaps 5 or 6 minutes, wherein we'll see what we mean by continuum, rigid body, a particle, a system of particles, an inertial frame, and force as a vector quantity. Let us begin by seeing what we mean by continuum. By continuum, we mean a continuous distribution of matter with no voids or empty spaces. For example, if you consider a body something like this body consists of several particles which are distributed. When we say these particles in the object form, these are particles in the object form a continuum, what we really mean is however small a neighborhood we take as represented by, let us say, a small neighborhood as represented by this circle. Within this circle, density of matter will be the same as that of anywhere else. Whether you take in here or here or here, or if you make it to be very small here, the density is going to be the same. If such is the case, we call it continuum. In actual practice, during castings or even in some manufacturing processes, there will be small pockets of voids. Those voids we'll ignore and we'll say that the body is continuum. You have particles everywhere and no pockets or voids anywhere else. Next is the concept of a rigid body. Okay. If you say that this body is rigid, what we mean is whatever be the nature of forces that are acting on it, different kinds of loadings or maybe pressure distributions or torques, whatever, distance between any two particles A and B, you can just take just about any two particles and the distance between these two particles remains the same irrespective of the loading that is coming onto this object. In real life, no object is a rigid body because every object deforms a little bit under the action of forces. But if the size of the object is very large as compared to the deformations that are occurring, then we say that the body, then we idealize and say that the body is rigid body. The third concept is that of a particle. When we say a particle, what we mean is it's a point mass. All the mass, whatever be the mass of that particle, all that mass is concentrated at one single point. And by definition of a point in Euclidean geometry, it has zero dimension, zero size. Okay. So strictly speaking, no mass, no object can be considered as a particle. But in some situations, for example, take the case of our planetary system with sun at the kind of center and planets revolving, let us say our Earth itself revolving around here. Okay, as compared to the size of the sun and the space in between, all this distance in between, as compared to the size of the sun and the distance in between, the size of the Earth is very small, maybe 1,000th of the distance in between. So in such cases, we consider Earth to be a particle. Similarly, in the case of a big automobile, a small bolt, 1/4 inch bolt, as compared to the total size of the car, that 1/4 inch bolt is really small and it can be considered as a particle. When you have several such particles modeled, for example, you have another planet orbiting here, you have one more particle here, you have another orbit, okay, you have another particle, and so on and so forth. If you kind of model a particular situation as kind of several particles, you will say a system of particles. Very many times the total size of the object may not be of real concern. In such cases, we consider the object to be a particle. Okay, we have also seen what we mean by systems of particles, and we'll see what we mean by inertial frame. When we talk about positions of several points, and when we want to specify where each of such particles is located, each of such particles or each of the objects or the centroids of those objects are located, we need to specify, in some sense, refer to some other object. Okay, for convenience, we will take one x-axis and one y-axis, and also if we want to specify z-axis, and refer the positions of every object that we talk about in relation to this x, y, z. We'll assume that this origin, the point where these inertial axes meet, we call it the origin. We'll assume that this origin is either fixed or it is moving in a straight line with constant velocity, and the directions of x, y and z axis remain same. If we have a particle, we may specify it, for example, to be in xy plane, and this distance as y coordinate and this distance as x coordinate. So once you specify x and y, the location of this point is fixed with respect to this inertial frame. Sometimes this frame is also called Newtonian frame, or sometimes it is also called inertial frame. Okay, so it is a good practice always to have this inertial frame represented on whatever drawing you make. So if you want to represent a particular situation, draw a inertial frame and refer everything with respect to this inertial frame. We'll try to do that all through this course. Once we have inertial frame, let us say we have an inertial frame only with x and y axis, okay, and you want to represent a vector f. Okay, we know because force is a vector, it will have a point of application, and then it will have a line of action, and it will have a direction. When we specify these three things for a force, we will say that the force is completely defined. For example, the first aspect, point of application, we can specify that the force is acting at a point with a defined value of y coordinate and a defined value of x coordinate. If you specify those two things, the point of application is specified. To define line of action and direction, we also need to find out what is the angle it makes with respect to any one of these inertial axes, either x-axis or y-axis. Typically we take angle with respect to x-axis and specify that angle. For doing that, we'll try to draw a line parallel to x-axis here and measure this angle in anti-clockwise direction theta. So when you specify that angle theta, the line of action is also specified. And the third is direction. You put a arrow head here, we call it head of the vector quantity, and we'll put a little tail here and we'll say this is tail. Very often we omit this tail, we just put this head. The tail is understood there. When you do all these three, we'll say that the direction of this vector quantity is completely defined. With that, we come to the end of this lesson 3. What we have seen is, we have seen what we mean by continuum, we have seen what we mean by rigid body, we have seen what we mean by a particle, system of particles, inertial frame, and force as a vector quantity. Thank you very much for staying and patient listening. Have a good day.